message M. And so my question to you is whether this is a secure, nonce-based encryption system. So the answer, as before, is yes, but only if the nonce space is large enough, so as we increment the counter r, it will never cycle back to 0, so that the nonces will always be unique. We argue security the same way as before. Because the PRF is secure, we know that this encryption system is indistinguishable from using a truly random function. In other words, if we apply a truly random function to the counter and XOR the results with the plaintext M. But now, since the nonce r never repeats, every time we compute this f of r, we get a truly random, uniform, and independent string, so that we're actually encrypting every message using the one-time pad. And as a result, all the adversary gets to see in both experiments are basically just a pair of random strings. So both in experiment 0 and in experiment 1, the adversary gets to see exactly the same distribution, namely the responses to all his chosen plaintext queries are just pairs of strings that are just uniformly distributed. And this is basically the same in experiment 0 and experiment 1, and therefore the attacker cannot distinguish the two experiments. And since he cannot win the semantic security game with a truly random function, he also cannot win the semantic security game with the secure PRF. And therefore, the scheme is secure. So now we understand what it means for a symmetric system to be secure when the key is used to encrypt multiple messages. The requirement is that it be secure under a chosen plaintext attack. And we said that basically the only way to be secure under a chosen plaintext attack is either to use randomized encryption, or to use nonce-based encryption where the nonce never repeats. And then in the next two segments, we're going to build two classic encryption systems that are secure when the key is used multiple times.